Well, I don't just want to single you out, Josh, but Josh had a great question last time, and that is, can the fractures be too closely spaced and deplete the reservoir? And so maybe I tried to address that last time, but maybe you'll see these 4 slides later on in your career, but it kind of addresses that question. You know lots about these systems already. You know that to be able to take heat out of the system, this is the relationship that we have, which, which is that the heat rate, joules per second, is a function of 3 factors, all of which have to be non-zero for them to work. The mass rate of flow, kilograms per second, and the temperature change between inlet cold fluid and outlet fluid, whether it remains cold or not. And so therein lies the challenge. So the challenge is this: you want to have a large volumetric flow rate. That's controlled by the permeability, as we talked. We'll talk more about that for multi-phase fluids in the week to come. Next week, we're going to talk about transitive fluids. Darcy's law requires a pressure gradient and a permeability. Permeabilities are typically very small, so constraints on crustal permeabilities in the middle of crustal areas vary from something like a Darcy, which would be this, 10 to the minus 14 meters squared, or rather vary from a micro Darcy from 10 to the minus 18 meters squared, and to get them to flow for geothermal rates, you need to maybe change those by 3 orders of magnitude. That's great if you can change them by 3 orders of magnitude, because it allows you to get more fluid through the system. But if you're not able to also have a residence time or heat transfer into that fluid fast enough for it to be able to warm up the fluid, the residence time, then you get cold fluid in and cold fluid out, which doesn't help you. And so the characteristics of these, people have talked about using, we know about hydrothermal reservoirs on plate boundaries where permeability is high and they're all broken up, so spacing between fractures is relatively small. EGS, in the middle of crustal areas, you have to make fractures. So the typical characteristics and the main components that relate to that is that you have to raise permeability from micro, 10 to the minus 6 Darcys, 10 to the minus 18 meters squared, to millidarcies, which is 10 to the minus 15. And so this is related to what we defined as this mass rate of flow. I'm not sure why this is small. That's better. And typically they comprise impermeable blocks of rock with fractures around them. But in sedimentary reservoirs, actually you have lots of porosity. So you're able to flow between the pore space. The porosity might not be less than 1%, might be up to 30%. Volume of voids relative to the solid that's in the reservoir. They might already be up to 10 to the minus 14, so you don't have to stimulate them necessarily. And most importantly, the other component which represents how the temperature can be changed. So mass rate is one, temperature is another. Those are the two that go into this previous expression we had on the previous slide, into this. This and this. And so these are the two challenges. One is making permeability large enough so you can generate fluid through it. And the other one is being able to have a heat transfer length, which is the spacing between fractures, and so that you can get enough heat sent to the fractures. Not a problem in sedimentary reservoirs because mass flow rates are typically high. Sometimes they're depleted petroleum reservoirs, so by definition you can get fluid out of them. But that doesn't say anything about the distance between fractures, but typically they're pre-fractured, they're shallower, they've gone through tectonic changes, and the fracture spacings may be much closer. And so if you want to be able to get heat out of it, one way you can look at, a very simple way to look at whether you can get heat out of it with a long residence time, is to look at the heat rate you can get from pumping a fluid through a system. And so that a volumetric flow rate, mass times specific heat capacity, and the temperature change between the reservoir and the fluid that's going into it. So this is the advective flux, if you like. And the other way is how heat is transferred from the blocks to the fractures that surround it. And so if you have this kind of broken orthogonal fracture set with spacing of fractures on the sides, you could imagine that the heat transfer out of that system to the edge is delta T, which would be the temperature around the block versus the temperature in the core, and the distance which it has to travel, which is, it's half of the spacing in this particular case, but that doesn't matter. And so what you could do is you could write Fourier's law. So the area over which it flows, so I guess the simpler way to look at this block would be to think of it as a length here, which is the spacing, a temperature gradient here, which is delta T. And so this delta X is really S over 2 because it would be coming from the center of the block, but let's not worry about that. And this is thermal conductivity, and then this is the cross-sectional area of flow. And so the cross-sectional area of flow is just, you'll see this slide later on in your career as well. It's just S by S. Each of these unit lengths here is S, S, and S. And so this is the gradient. And so if you combine those together, you could write that area is equal to volume divided by S, right? Volume is just S cubed divided by S, or volume is S cubed. Divided by S gives you an area. So that's where this comes from. Thermal conductivity, delta T, and this S from here, and also S from here. So you get a very convenient non-dimensional number. So these are dimensional, I guess. They're not non-dimensional. But you could look at the ratio of those. So if you look at the ratio of how much heat is carried by the fluid and how much heat is carried by conduction. If the heat carried by conduction is very small, then it's not a very efficient heat exchanger in getting heat from the solid into the liquid. And so you can just take these two expressions, divide one by the other. You get a non-dimensional parameter, which is specific heat capacity times density of the water, thermal conductivity of the rock, volume of each of these components, these blocks, and a volumetric flow rate and a characteristic length. So since volumetric flow rate comes here, you can call this, it has to be dimensionless, right? Because these have to have the same units. And so it'll work well when HS is large, and therefore this overall term QD is small. So that's exactly the condition we want. If you look at how heat would be transferred in a reservoir, if you inject fluid at one end of a reservoir and go across to another outlet borehole, then if the heat transfer within the reservoir is not efficient, then you'll inject cold water. It'll go across the reservoir and it will gain a little bit of heat. This is the small amount of heat that it's gaining, would be this amount here. This is delta T. But it would come out only slightly warmer than it went in. And so this is a very inefficient reservoir. And then this is when QD is equal to infinity, the opposite of this, right? So that's exactly what you don't want. If you have a reservoir where the characteristic dimension is so small that this number becomes QD also becomes very small because the S is in the numerator. You can think of it as being a porous reservoir with the grain diameters being millimeters in size. Then what that would do is you'd inject at a cold temperature, and what it would do, the temperature of the fluid that's flowing would physically, if I can get this, it would physically rob the reservoir of this depleted temperature. So the amount of heat that would come out of this would be equal to its volume times rho times C times delta T. So delta T is this full thing. Its volume is going to be the length into the reservoir and its physical characteristics of this. And as it continues through the reservoir, at time T2, the plume would look like, whoops, it would rob the next part. And then time 3, it would just advance as a single plug. So it would take all of the heat out of this portion of the reservoir. It'd exchange it into the liquid by warming the liquid up to the temperature of the reservoir, and then carry it through to the outlet, in which case you can recover it. And so if you look at the exact time series of what would happen at the outlet, you could imagine that there'd be no change in temperature at the outlet until this cold front breaks through. And so if you plot the temperature change with time, and you can define a time also in terms of these non-dimensional parameters, when this breakthrough occurs to this point here, then all of a sudden cold water would come at this point here. And the temperature history, time history, would be this line that you have here. If you look at the progression of this, then this gets cold water out slightly warmer than the inlet at early time, so that's here. And as time continues, it merely depletes the whole reservoir by a small increment by pulling fluid out of it. And so the trajectory of that would be this over time. And so you'd expect that if you plotted this in log time, the area, not in log time, in natural time, then the area under the curve that gives you this should be actually the same as for the plug flow reservoir, which is this area here, the whole area here. Because this is, by the time it's depleted down to this, you're taking all the heat out of the reservoir. In this case, you're incrementally moving it out so it stays warm, and we know that the hotter the recovery temperature is, the more useful it is, both because the ability to flash to steam is above 100 centigrade typically, and also because we know the efficiency of these equipment is higher if we have higher temperatures. And even though it depletes suddenly, it would have depleted all of the thermal energy in the system. There are a couple of, or a number of models that represent this behavior. The reason why you'd expect this delta T maybe in the initial phases to be large is because if you think of the face of a block, which is, so this is the face of the block where the temperature is escaping into the water, which is flowing past it, then you know that the gradient that develops at this boundary would initially be no drawdown at all at time 0, and then at a little bit of time it'll go to look like this, and at later time it looks like this. So this gradient here is dp dt, or dt, change in temperature with length. And so when this is very close to this, so this would be temperature here. So when this is here, it's infinite. So initially, when you start depleting, this temperature gradient is infinite, which means that the heat transferred from the solid is also infinite, but only for an infinitesimally small period of time. And then once it gets depleted, then the gradient of dt dx is progressively smaller and smaller and smaller at this interface, and that's what controls exactly the heat flow out into this. So as time goes on, it gets a shallower and shallower gradient, and so the difference between temperature inlet and outlet gets smaller and smaller because it gets less and less efficient. So confirming models basically show this as well. If you have a very short spacing between fractures or a very small flow rate, then the depletion, this is given in temperature. So this is reservoir temperature, and this is the influent water temperature, non-dimensionalized. And this is a non-dimensional time, bless you, similar to the one that we mentioned here, which allows you to scale. So when the fractures are very closely spaced, it tends to be that this is exactly the performance you get. Stays hot at the outlet until the breakthrough occurs, and then it goes to zero. If the fractures are wider and wider spaced, then it goes in this direction. Likewise, if you look at different models for this, you get similar behaviors, just different models. So the point is, too small, the spacing is never too small. All it will do is it will allow you to deplete through here. And I guess if your flow rate is so large that you move through here and this front arrives at the well in 1 year, all you need to do is space your wells 30 times further apart. And so the longevity of the reservoir will last 30 years instead of a single year. So that's right. So I thought I'd mention that. I appreciate questions. Okay. So back to thermodynamics. So we've talked in detail about the thermodynamics because we need to use it for a couple of things. We need to flash the steam to be able to get mechanical work out of turbine machinery. We need to understand kinetics and chemical deposition in reservoirs, which is controlled by thermodynamics. And we also understand that the heat that we get out of a reservoir is controlled by the transfer of fluids. And those fluids may be liquid as water, or they may flash to steam depending on how we deal with it. So for those of you who've had the misfortune to take EME 303, what we've said so far actually is really not very different from what we've dealt with in that. If you remember when we talked about the first law in this class on Tuesday, 2 days ago, we had this figure that said that the heat flow into the system, work out of the system, and change in internal energy in the system is given by the first law. And we quoted the first law as being heat rate minus the work is equal to the change in internal energy of the system. So that is actually one way of putting it. When we talked about this in fluid mechanics that drives this together, we used something called Reynolds transport theorem. We looked at the heat flow into the system. We looked at the heat work done in the system. And we looked at the internal energy that was contained in the system in terms of this parameter E. We looked at changes in those systems in terms of the heat rates and work rates out of the system. This might be small. I don't know. I don't know why it won't get bigger. It's interesting it doesn't. We could define this internal energy in terms of both flow rates and elevations within the system. These probably don't matter for us in what we're doing here. But the internal energy was defined in terms of internal energy plus pressure over density. And this pressure over density is what we've called before pressure times specific volume. Specific volume that we defined was equal to just to 1 over rho. So density is in kilograms per meter cubed, so it's increasing specific volume is the same as increasing actual volume of an expanded fluid if it flashes to steam, for instance. So we can define this. And we tended to use a very specific sign convention in that the sign convention for both heat rates and for work rates was defined positive if it was energy put into the system. So this, in our case, would be heat in. This is work out equals internal energy. And so if we define it here, it's heat net in plus work in equal to changing internal energy in the system. And the way that we defined it was to define it in terms of these two terms were combined in terms of enthalpy. So we could write it as a streamline. So I guess we drew it as a streamline, which would be this. And we could define flow within the system relative to that streamline in terms of upstream and downstream, locations 1 and 2, velocity out of the system, velocity into the system, an elevation of this point relative to a datum, which we haven't worried about very much. This is drawing things with a very thick C2 to this point here. And pressures, P1 and P2. So rather than using just a box, a zero-dimensional model, stuff going into the bucket, stuff coming out of the bucket, it's no different from what you can do if you write the energy equation in terms of a single streamline. This now happens to be the bucket, but it also has fluxes of velocity and elevations included in it, as well as this component here. And we can look at mass rates of transfer into and out of the system. So it's actually, it seemed maybe that we were doing something different from what we would do in that kind of configuration, but we're not. This is our, I guess this is our 1D model. And this is our zero-dimensional model. 0, not O. And as a result of that, we get those behaviors. So that's perhaps worthwhile mentioning just because to put us on the same page. If we look at the other things that we've talked about, so in terms of characteristics that drive these, so we're not going to spend all the semester talking about the heat engines that are a system, but it's a useful vehicle for us to discuss energy and work in these systems. Mainly we'll be dealing with the subsurface behavior. So we can define enthalpy as internal energy plus pressure divided by density, which is equal to the same as internal energy plus pressure times specific velocity volume. Lowercase v was equal to 1 over rho. This would be of the fluid in this particular case. We can define our first law in terms of a mass flow rate in. So mass flow rate in would be equal to area times velocity times density, just as in terms of kilograms per second. If you multiply an area times a velocity, it's meters cubed per second. Kilograms per meter cubed ends up being in units of kilograms per second. And so a mass rate flow into the system, enthalpy, velocity, elevation between inlet and outlet, and the definition of heat rates and work rates, both defined as putting positive as put into the system. We can define efficiency. We did last time. We defined efficiency as if we look at the work into the system, which is the difference between the net heat in versus the net heat out, divided by the net heat in. It's equal to efficiency is equal to 1 minus T out over T in, or delta T divided by T in. So the system is at very high temperature. If when you take fluid out of the system it's at a lower temperature, then the ratio of these in absolute temperature. So these have to be in Kelvin. Talked about it last time. And we did an example last time, I think, in terms of water at critical temperature, change in entropy. We did an example in terms of coming out 100 degrees centigrade and the temperature drop being to 0 to 100 versus 400 Kelvin. Well, this is 100 centigrade to 0 centigrade, but we also did it in terms of critical point of water down to 0 centigrade. And we saw that the efficiency of the system was, instead of being 1 minus 3/4, which was 0.25, it ended up being larger than a half. So we talked about that last time as well. And we went through an idealized picture of exactly a Carnot cycle to define behavior. And this comes out of Glassley's book, which I looked at yesterday, available free online. And this is the Carnot cycle going from a compressed fluid which has small volume, present here, allowing it to expand by gathering a small amount of heat. So this is the volumetric, not volumetric, this is the change in heat input in the system. It's positive because it's into the system in our sign convention. And this allows it to gain enthalpy. Once it is heated, then it is allowed to expand. So it gains heat, it expands with that heat. By expanding, it puts work out of the system. And so work out of the system would be negative by our sound, not positive, which allows it to be running it through a turbine. So it expands and runs through a turbine, comes out the other side as a vapor instead of as a liquid as it started out. So by the time it gets here, it's a vapor. Then you take this and you take heat out of the system. So Q out is negative Q by definition. So in condensing it, you take it from a gas and remove heat to make it to a liquid again. As it becomes a liquid, it gets a higher density, so it's a smaller volume for a given mass that's locked in the system. And then once you get it to be condensed, then you provide mechanical work into the system. And that would be positive to be able to get it back to the same enthalpy that it had at the beginning of the cycle. It goes through this enthalpy cycle from this point. So we did it before in terms of a phase diagram for water. This, in our previous case, was temperature rather than pressure. Here we've defined it in terms of pressure. And so this occurs at no temperature change. As you remember, we went horizontally. So no temperature change, but accepting heat into the system to change its enthalpy, then allowing it to expand, expanding, using that expansive power to do work. So you're taking work out of the system. Then you take heat out of the system of the steam to be able to condense it, to take it down to a smaller volume. and then you provide compression to be actually be able to get it to the same density as it was before, as liquid water. And then you can repeat the cycle. So that's the definition of our system. Okay, so I'm not going to talk. We can talk about Gibbs free energy. I don't think we use it much in the future of what we do. So Gibbs free energy is just used to be able to say something about the state of a system. And it is used to be able to say something about the direction that chemical reactions would go as well. And it defines the state of a system. And it really relates to a change in enthalpy in terms of, this is the expression. For a closed system, we lose all these latter terms. But this is the change in enthalpy at one particular pressure and temperature. This here. This is at a given particular temperature. This is the change in entropy that occurs in terms of disorder of the system. And by using each of those, you can define a parameter, which is Gibbs free energy, which denotes the changes in the chemical state of the system or the thermodynamic state of the system, which can be used to talk about the energy in the system or the rates at which reactions progress in different minerals. So I'm not going to say anything more than that other than to define this and to make the point that if you look at the changes in Gibbs free energy, which are enthalpy minus temperature times entropy, you can define this in terms of work per mass, per kilogram, or work per mole, if you do it on a molar basis. And if you look at the change in Gibbs free energy as you change temperature, say within water, for which this is, then if water is liquid and if it's present at either 0.1 of a megapascal, so this is 1 bar, and you look at how its Gibbs free energy changes as it goes from 0 centigrade to 300 centigrade, then the change in Gibbs free energy is relatively small. If you look at, for a vapor, how that Gibbs free energy changes as you go along the same temperature, the change in state, Gibbs free energy of that state, is much steeper. It's much more sensitive than liquid to that. These crossing points for when it's a vapor at 0.1 MPa, 1 bar, relate to 99.9 degrees centigrade. This is the boiling point of water at 1 atmosphere. This, where it crosses from water to vapor at this would be the boiling point of water at 10 bars. 1 MPa is just 10 bars. This is 1 bar. So the intersection between these Gibbs free energies is where you'd come along this trajectory here, and this steeper trajectory, this change in Gibbs free energy, would be larger. It would take this path instead of continue on as water. So as it got up to the boiling point, it would then turn to vapor, and it would carry down this trajectory. If it was under higher pressure, it would remain as liquid for longer before coming vapor as it crosses this point. So it allows us to say something about the state of that behavior. But we can also say that those changes in state by looking at the so-called phase diagrams for water. We talked about thermodynamic efficiency. We did that twice. We talked about it today. If we plot thermodynamic efficiency, so if you worked out exactly what the initial state of the system was in going to a lower temperature, so this might be a geothermal reservoir at 100 degrees centigrade. You take the fluid out and it goes down to a background temperature of 20 degrees centigrade, which would be a normal ambient atmospheric average temperature. Then you can calculate exactly what this efficiency becomes. It's 1 minus delta T over T0. And if you do that for different initial temperatures, so if you plot this curve, say you have a reservoir that starts off at 250 degrees centigrade. If you take it to the surface and run it through a turbine so that when it comes out of that turbine at 65 degrees centigrade, so these happen to be in degrees centigrade. In this you have to use degrees Kelvin because it's absolute temperature that has to be used. And so this is a plot using that. Then the efficiency of that particular system would be something like 35 or 36%. If you flash it to steam in the turbine and it goes to a background temperature of 20 degrees centigrade, then the efficiency is now 44% or 0.44. And so the lower this becomes, the better it is, because these successive curves go higher and higher. Of course, this is the limit if you're bringing things to the surface and flashing it in a current environment. So the only way that you can get it to be more efficient would be to use a reservoir that's much hotter. So the critical point of water is something like 360. So if something is supercritical, it's not a limit on the temperature, but a supercritical reservoir, if you flash it and it goes to 20 degrees centigrade, then instead of being merely 44% effective, it would be something like 55. And if it's even hotter, then you go further up. So you can define exactly the efficiency of the reservoirs. Those are just definitions of the efficiencies that come off that plot. And finally, or not almost finally, you can think about these things in terms of the geometry of a reservoir. And so if you look at a phase diagram for water, so this is temperature in degrees Kelvin. So 207, this is roughly 0 degrees centigrade. The freezing point of water, triple point. And so this is the behavior of water superposed on this pressure of water versus the temperature of water. So this is the triple point. This is liquid. Sorry, this is solid. Solid, liquid, and vapor. I guess these are all marked on here. In terms of this curve here being one boundary up to the critical point, and this being the other boundary from identifying ice, water, and vapor. So it's a well-established curve. So what we could do is we could take the crust, and we know that if we go down with depth and we look at the change in pressure, that pressure increases with depth, and that change in pressure is equal to P is equal to the unit weight of the material multiplied by its depth. So at any particular depth, the pressure is given by that. If we want to calculate the rate at which pressure builds, we can rewrite that in terms of density and gravity and the depth. And we said before that if we have water, density of water is 1,000 kilograms per cubic meter. And so the unit weight of water is equal to roughly 10 kilonewtons per meter cubed. So this is how the pressure of water would change as we go down in depth. If we take rock, we said before that the density of rock is typically of the order of 2,700. kilograms per meter cubed. It's about 3,000 of that order. So if you look at the unit weight of rock, it's of the order of 30 kilonewtons per meter squared. So if we go down 1 kilometer, say, then at 1 kilometer, the pressure of rock is equal to 10 to the 3 times 30 kilonewtons per meter, cubed, right? Cubed. So 10 to the 3 kilonewtons per meter cubed times 10 to the 3 meters equals 1 time, which is 30 times 10 to the 6 newtons per meter squared equals 30 MPa. So at 1 kilometer depth, the weight of rock above you is 30 MPa. At 1 kilometer depth, that's important because at 1 kilometer depth for water, since it's a third of the density, so at 1 kilometer for water, that would be 10 MPa. So if we have, on this graph here, if we look at how the pressures vary with depth, so 1 would be for water, 1 would be rock, this would be 1 over unit weight, one over unit weight of water. And so on this figure here, you could equate 10 MPa would be equal to 1,000 meters of water. $30 MPa would be 2030, so this would be and so this would be 1 kilometer of rock. So all I'm doing here is this scale here in meters is in meters of rock equivalent. This scale on the right-hand side is in meters of water equivalent. And of course, we don't have a scale on the other side, but it's roughly going to be 3 times. If this is rock, this is a third, so this would be 10,000 meters. This would be 100,000 meters, etc. Make that large. So the only point is that we're trying to convert a pressure, which exists at depth, to an equivalent depth. So you could write this as being, this would be 30,000, this is 30 kilometers, this is 3 kilometers, this is 0.3 kilometers of rock equivalent. So these pressures represent some depth. So you can convert these pressures, which represent the phase diagram. So this represents the phase diagram in terms of pressures. And we know also, as we go down in depth, if I go down here, we said also, I won't overprint it on the same figure, but it is the same figure. This is temperature, with depth. And so this is either 50 degrees centigrade per kilometer equals 50 Kelvin. Uppercase K, not lower. And this would be 25 centigrade per kilometer. So, all by way of saying, if we choose a particular depth, which may be a kilometer or not, then we can get a temperature from that. And if we have these two geothermal gradients, potentially we have a bracketed value of temperatures. I guess this would be T max, and this would be T min. So we can calculate what those are at all depths as we go down in here. There'd be no difference between them at 0 depth, and there'd be a big difference between them here. And likewise, as we go down, if we look at either the rock pressure or the water pressure, we could choose those, and we could choose one of those to represent the pressure at which we have a corresponding temperature. If we look at the the variation between the magnitudes of pressure that we might have would be the so-called hydrostat. So if you go down in a swimming pool, this is the pressure you'd feel. If you go down in a geothermal reservoir and the water is filled to the top and you go down a kilometer, this is the pressure that you'd sense 1 kilometer down, which will be at 10 MPa. This would be 10 MPa. So this would be 10 MPa, and this would be 30 MPa. And the significance of this is that if you provide a pressure in the reservoir which is larger than 30 MPa, you fracture it. You hydraulically fracture it. You can't sustain it because the pressure in the water pushing against the rock will just lift it up and hydraulically fracture it. So all by way of saying is that for any particular depth, we can calculate a minimum and a maximum temperature. We can calculate a minimum and a maximum pressure given by the hydrostat or the lithostat. Lithos is being Greek for rock, I guess. And that bounds these values here. So I'm not doing this. So this diagram is just culled from this. And what it represents is that at any particular elevation, say 30 kilometers, there's going to be a range of temperatures which we could expect to have, and it's based on the geothermal gradients or the span between them, 25 per centigrade per kilometer or 50 per kilometer. And likewise, we get a span in terms of, at any particular temperature and depth, we get a span in terms of pressures, because that is this span between these. And so that shaded line here represents the bounds on that as you go down deeper in depth. That's what we're doing. And so this is the conditions that the reservoir would see. Those conditions suggest that in all states the behavior would probably be liquid because it sits between the vapor phase and certainly not frozen. And these represent overprinted magnitudes of these individual zones here, which are the region which is available for flashing water to steam. So all of this is in degrees Kelvin. So boiling in degrees Kelvin is 375 or 373. So this is boiling point. So if you want to be able to generate electricity, you like to be able to flash to steam because it's the phase change we use in a turbine to do that. It exists slightly below that because you can actually use what's called a binary system. So you have water that comes out at 120. You flash it to steam, it ends up being at 100 degrees centigrade or less. And then you use that to transfer the heat to a different fluid, say isopropanol, which boils at 40 degrees centigrade. The heat's transferred to that in a closed system. It boils the isopropanol, that runs through a turbine in a closed system. It's collected, condensed, and then turned back to liquid again. And so it means that you can actually get electricity by flashing fluids, water to 100 centigrade, and some other fluid down to maybe about 40 centigrade. So this zone here is the region that is for power generation. The region which is for direct heating would be this. So slower, lower, and typically at lower depths. So it's not as deep as geothermal reservoirs, which might go to 4 kilometers. This might be somewhat less, and it's quite a lot less because this is a log scale, right? So this is, if this is 4 kilometers, then this would be 0.4 of a kilometer. So I guess if this is 30 kilometers, then this is 3 for the system. And for ground sourced heat pumps, which is this lowermost block here, which is defining here. So ground sourced heat pumps, direct use, and for electricity generation, for power generation. These all sit within the liquid part of the phase diagram for water. It's above the vapor temperature, below the vapor temperature, and above the frozen temperature. And so that's really just bounding what the expected conditions are for temperature and pressures as we go down in depth. And that's that. What else? Finally, I guess, those behaviors in terms of pressure and depth. So if we know now what the pressures and temperatures are, so the point we've made here, that as we go down with depth, we have both an expected temperature and an expected pressure. And so what we should be able to do is we should be able to define the enthalpy that exists for those same conditions. And so those conditions are given here. This is the block for ground sourced heat pumps. This is the block now for direct use, which is this square portion here. I guess they're the colors rather than the lines. They're bounded by lines. And the part that's for power generation in geothermal is something like this, bounded by this. So those are the different utilizations, I guess. Power, direct use, and ground sourced heat pumps, just as on the previous figure. But the other item that looks on this are the isotherms. So instead of having pressure and temperature drawn out in this form, pressure and temperature and the phase behavior of water, now we're plotting pressure and temperature and looking at the phase diagram. So you see these individual kinks here. This and this and this. If we join those, I guess I'll just join them as straight lines because I can't draw curved ones very well. And I'm making this one up. And if you look at these other kinks here, this and this and this, and I join those up where they join at this particular point here. I can't do it very well to turn it on its side, but this blue line would be, if I write in liquid, and I go off somewhere here, and if I write over here vapor, So this is pressure. This is increasing temperature, 50, 100, 150, 350. So you'd expect as you go up in temperature, the liquid water would turn to vapor at some stage. So these little kinks in the isotherms are phase changes within the system, going from vapor to liquid. And as you go from vapor to liquid, these are an isobaric path, I guess, across the system. No change in pressure, has to be, right, because this is a constant pressure as we go down through here. And these represent a system that we've seen before. And that system is right here. So if you take this figure here, which is, and what do you want to do to it? You want to shift it so that this side here goes here, and this side here, which is enthalpy, goes here. So all this phase diagram is, which we use for the Carnot cycle, by the way, is exactly this behavior plotted in a different way. So this is a phase diagram. So as you go from at constant pressure, if it's heated, then you'd go across here at constant pressure, and you'd turn water from liquid water to vapor. So that's exactly what we're doing here. So we can explain exactly what's happening here. Is that if you start in a reservoir which has a pressure of 1,000 bars, so 1,000 bars equals what in pressure is 100 MPa. 1 bar is 0.1 MPa. You might remember. It's 100 kilopascals, in other words. So if you start off in a reservoir at 100 bars, so 100 bars would be 100 MPa, so this would be something like 3 kilometers, I guess. I think that's kind of what we said here, not in this figure, but on this figure. Yeah. 3,000 meters at 100 megapascals. And so what happens if we flash, if we bring that to the surface? So we're sitting nicely down at 3 kilometers, which is what this is right here. If you bring it up to a pressure of 1 bar. This is atmospheric pressure. So you bring it up to the surface. If you bring it up quickly, it has no time to respond in terms of the pressure of the fluid and the enthalpy of the fluid. So you come down to this point as a liquid, and then you have to make a decision as to whether it goes down on this path, whether it can climb here and go across the top, which of course it can't because it has to have some energy put into the system, or whether it changes so quickly that it doesn't have time to change its enthalpy or the pressure that's acting in the system. Can't lose energy from the system. So the chances are that if it's brought up to the surface very quickly, it will come up with this amount of enthalpy in it, which is the amount that is existing in native form. But when it comes up, it will have a different composition because no longer will this be 100% water and 100% steam, but it will be given by some ratio between the middle. And so to get the proportion, you could just read off the proportion of exactly what it would be here. And so what are the proportions of these two? It's going to be something like, this is 100% water, so it's going to be something like %70 liquid and 30% vapor. So in other words, this is 100% water, 80%, 40%, 80%, 60%, 40%, 20%, 0. And this is 100% vapor and 80, 60, 40, 20, 0. So this is done in terms of percentages of vapor. So that's fine. So that defines that as you bring it up, the enthalpy of the system is equal to exactly that which it began at, which is equal to, so the enthalpy, which we've called H bar, is equal to 1,000 kilojoules per kilogram. And you can do that because you have this figure. If you don't have this figure, however, and you only know what this enthalpy is, and you don't know what these percentages are, you can get that from merely writing the magnitude of the enthalpy at this particular point. So it would be enthalpy at 100 MPa. You've seen this equation before, is equal to X times the enthalpy in the liquid at 1 bar plus 1 minus X times the enthalpy in the vapor form, also at 1 bar. And so in this, it's actually different from how we did it. We did it before that X was equal to, so in this particular case, X is equal to the mass of liquid divided by the total mass. And 1 minus X is equal to the mass of vapor divided by the total mass. I'll just remind you, you don't know if you remember or not, from last time, we merely defined a way to be able to map between systems. Went through this little derivation, and we said that the specific volume was equal to the 1 minus the mass of the fluid times the mass of the gas divided by. So we defined it in terms of mass of vapor divided by the total mass for X. We've just done it the opposite way. And this is just merely mapping across the phase diagram, going from pure liquid to pure gas as we go across it. It's just this X plot. And so all we're doing there is exactly that. We're utilizing that relationship, although we've defined it in concert with Glassley's book. And so if we know what the enthalpy is at depth in the reservoir, if we know what the enthalpy of liquid water and steam, I know it just disappeared, if we know what each of these are, and if we know what this is in the reservoir, we can go and we can calculate the value, the relative proportions of gas and liquid in the reservoir. That's done here because it's contoured in terms of those plots, but if you only knew this magnitude here of enthalpy, this magnitude here of enthalpy, and this magnitude of here at enthalpy, which is given on this table here. This is properties of water, this is temperature, this is pressure in bars, this is enthalpy of vapor, steam, enthalpy of liquid. So if we go down to the particular temperature we found ourselves at, then we find the enthalpy of the vapor is 76 kilojoules per kilogram. We know the enthalpy of water is 419 joules per joules per gram, I guess, in this particular case. And we know when it first comes out, it's purely at liquid state, which is this. It's at 250 degrees C, which is this which is going from this point here to here. So this is where it hits this contour at 250 degrees C. It's traveled down it, 250 all the way, comes down here. So now, since we have these magnitudes of enthalpy of liquid and vapor at these two states, we have enough to put into this equation for this, and this, and this. One equation and one unknown, we can solve for x. And so that's dealt with down here, exactly that thing. Comes out of Glassey's book. That's exactly it. The only difference you have to be aware of is that this x is equal to the mass of liquid divided by the total mass, rather than the other way around. And this is the calculation here, and it comes out to be roughly, if you solve for x, the value you get should be 70%, and by definition 1 minus x is 30%. So we'll leave it there. So that's all I've got to say, I guess, in the big picture for what we did today. Well, we did some examples and showed how phase behavior fits into the column as we go from low depth to shallower depth. That's what would happen if you bring fluid out of a geothermal reservoir and put it through a Carnot cycle, through a turbine. So we understand something about the mechanism by which we can get work out of that system. And I guess we also made a point that this idea that when we talked last time using a different terminology, that we used the fact that the statement of the first law defined heat in and work out with a change in internal energy, then that's why we could write it as heat in minus work out is equal to the change in internal energy, which is enthalpy. And so that's represented through the first law, and it can be applied in 0 dimensions. We have to be careful about the sign convention, which is chosen this way. It can be written as a one-dimensional problem, which is this, where the mass rate per unit mass, I think, is what's given here. This is enthalpy between in and out. This is velocity across the boundaries. And this just represents a one-dimensional system, in which case, instead of being a bucket where we put things in and take them out without regard for anything other than the plus or minus sign, here we have the possibility to be able to get fluids traveling out at a given velocity, and the velocities upstream and downstream changing along with elevations. So this is a more complete way of doing this. This is what we did before, and we have to be consistent about the sign convention. This was in positive and out positive, so that was our statement here. This is defined so that in and are both positive, and so they're additive instead of linked with a negative value. So you just have to be careful with the sign convention. So that's all we'll talk about today. So the next thing we'll talk about is what we started off with today, and that is the idea that in pushing a fluid through a system and allowing heat to conduct to that system, we're able to pick up thermal energy. It's manifest as a change in temperature in the heat transfer fluid. And so if we want to understand exactly how that can happen, then we should look first at being able to define exactly how fluid will go through the system. And so we'll talk about Darcy's law, rates of fluid transport in the system, and specifically about flow of fluids as two separate fluids. It can be liquid and it can be vapor. They can coexist and they can both flow, or it can be only one phase that's in the system. But the most difficult problem that we'll deal with is representing it as a two-phase flow system. Okay.